Okay, guys, chapter 7. Chapter 7 is very important chapter because it's dealing with solutions. So, talked about solutions. Well, the definition of a solution is a homogeneous mixture. Solution is, that's very important. Solution is a homogeneous mixture. Okay, guys, this homogeneous mixture is made of two components, made of two compounds or ions here. One is called the solute, second one called solvent. So the solute is a compound that can be dissolved in a solvent, correct? And its amount is very limited, small amount, not that much. Can be dissolved in the solvent, and it has a small amount or limited amount, limited or small amount. Okay, so you take the solvent here. Okay, let me take the solvent here, guys. And the solvent is a compound that has the ability to dissolve the solute. So it has the ability to dissolve these solute, and it is in large, it says large amount, and it is found in large amount. We'll make an example here. I have sodium chloride dissolved in H2O. This is a homogeneous mixture because ionic compounds are soluble in H2O, in water. So if you look at this, if I have this as being a solute, say I have of this 15 grams, and this is as a solvent, I will have 555 grams. So this is large amount here. This is small amount. This is small, and this is large amount. So, and they have to be what? They have to be dissolving each other. So, can I take this one out? Everybody has it. If you don't, take snapshot of it. If you don't, take snapshot of it, and it will be inside the iCollege and as the lecture. I mean the iCollege as a video, correct? So let me take this one out and just get to the idea. A lot of students think that solution is always polar because the solute like dissolves like, and that's misleading, correct? That's a very large misleading concept. So we say the solution is a mixture, correct? Solution is a homogeneous mixture. That's correct. But it can be polar solution, and we'll go in, or it can be non-polar. So don't come to the idea that all solutions are polar. No, that's not true. So if I have oil, as you'll see in the lab, plus cyclohexane, for example, this is an experiment, you'll see it today, I think, cyclohexane, ANE. And here I have sodium chloride or potassium chloride with H2O. So this is ionic compound. Ionic compound are soluble in H2O. However, oil is not soluble in H2O, but soluble in cyclohexane. So this solution is a solution too, but it's non-polar. This is a solution too, but it is polar, depending what you have of the whole thing. Don't come the ideas, when I say solution, it's always polar. No, there are plenty in organic chemistry, plenty of solution you can make. They are non-polar, correct? Most of the organic compounds are non-polar, not soluble in H2O, for example. Okay, so this is just the whole thing. Now, let's go and classify types of what? Types of the solutions. So, can I take this one out? Who has it? Make a picture of it. Make a picture of it. So let's take this one out. So now, what are those classification of solution? Well, we can classification of solutions. Well, we can classify the first thing according to their solubility, polarity, according to their polarity. So the first thing is solution is classified according to polarity. As I said, give you example, polar, non-polar, correct? Solutions. Number two, if I have the polarity, then I can look at the surface area, correct? I can go for surface area. Surface what? Area. So surface area means let me take surface area. So particle size. So let's particle size, which is really surface area, correct? I'll press it this one here. So to be consistent, according to particle or particles sizes or size, which is surface area, correct? At the end is its surface area. So number three, we look at the maximum according to their maximum solubility, according to the maximum solubility. Okay, guys. According to the maximum solubility, according to polarity, according to particle size. Number four, according to their osmosis, and we missed maybe one. According to the osmosis. Okay, number five, I think we might have put two together. So according to polarity, correct? According to particle size, suspension, we have colloidal. According saturated, supersaturated, unsaturated. According to osmosis, and it's just the one is. Let me just look at this here. Just bear with me a little bit. Why is this? Well, we had, just bear with me a little bit. Where is, yeah, it is. So the classification is, here they are. As you see, polarity solution can be classified polarity, electrolytes and non-electrolytes. Okay, that's good. So then we'll say number five, electrolytes according to electrolytes. So let's go one by one. Okay, so we went through the polarity in a couple of minutes, but we'll repeat it again. So we can have all this type of classification of a solution, which is really homogeneous mixture, correct? Made of solute and the solvent, 5 ones. Let's go one by one. Okay, so I will keep this one here. Just keep it here. I'll snip it then, so I can have it. Let me snip it here just for us, so we can go and look into it. Whatever we are missing will be there. So let me just take this one out here. I'm snipping with the snipping tool, and now I can take it out, but I have a background of it. So everybody has it. 5 different classification or categories or types of solution. So categories, types, correct, classes. So can I take this one now out? Can I take it out? Sure. Okay. Everybody has it? Okay. So we'll go first by one. First, according to what we said, according to their polarity, correct? I have to make the every time color change, because otherwise you will fall asleep on me once, twice, and then you will feel like you are not Wednesday, or you are what? You are still in Monday mood, correct? So the first one here, according to their polarity. According to polarity. Well, there is a rule. As I said, we have polar non-polar solution, which is the rule which we learned today, like dissolves like, meaning polar solvent or polar solvent dissolves polar solute. This is A. Let's take B here out. Let's put B here. And B here, non-polar solvent dissolves non-polar solute. This is none. And again, I have to apologize every time about my chicken writing. So that's not English. That's a German saying. They said if you have bad handwriting, it's not bad because it's just up straight and you write on the wall. It's very hard. So anyway, so this is the first one. And we had an example of this here. Let's take an example of both. The polar solvent, like you will see in the lab today, will have H2O, two things here. H2O with the potassium nitrate, that's fertilizer, correct? And H2O with potassium permanganate, correct? So all those here, you have ionic, correct? This is ionic. So ionic compounds are always polar, are polar, correct? Those are two solutions, 1 and 2, two polar solutions. However, we have two nonpolar solutions, which is here we'll have solvent is cyclohexane, nonpolar. Cyclohexane, we'll mix it with oil. This is very nice. When I say solutions homogeneous mixture means if you look at the solution in the test tube, you will not see two layers. You will see what? One single layer, not two layers. So, cyclohexane with oil or cyclohexane with iodine. Iodine crystals. This is non-polar. This is non-polar. Non-polar. And the solvent is cyclohexane non-polar. So cyclohexane is not polar. So like dissolves like means you have to have them the same polarity. The same polarity. You have to have them on the same polarity. And when I say polarity and you get to the idea, polarity produces what? Ions, which can conduct electricity. So let's put this one here, this note here. Let's put here the tab polarity produces ions, which can conduct well, it is electricity. Okay, electricity. So that's the first type, correct? That's what? That's the first type. Everybody's following? Let's take this. Everybody has it? Everybody has it back there? Take snapshot or you have the video. I know somebody will not watch 1 hour video, get tired. If you have attended, you will not feel to. But if you are not attending for some reasons, you are absent, so you can afford yourself 1 hour after lunch, whatever, to watch like you are watching a movie. Of course, watching chemistry is not watching a movie. Of course, you know that. The movie will not be bored, but chemistry, when you watch it for 1 hour, you get very, very bored. After maybe 10 minutes, 15 minutes, you are gone. Mentally gone. So anyway, so can I take this one out? Take it out? So now we'll go for the second one. The second one we have the back here. According to particle size, okay? Let's go according to the particle size. Let's minimize this and get this one here. According to their particle size. Number two here. According to particle sizes. Okay, guys, so according to the particle sizes, we have three, really two, but we can't say three. We have a normal solution, correct? With this, the solute. Always we are looking at the particle size. The solute has a very, this is number one, or A. A. The solute has very small particles. So, or it has small particles. This and those particles cannot be seen by any means. Which cannot be seen by any means. Okay, so it means by an eye. It is by an eye or by exposing solution to the light, or exposing the solution to the light. So I'm exposing this to the light. If the particle is moderate in the particles, not very tiny, okay, very small. So here it is, very tiny, cannot be seen by an eye, by the naked eye, or cannot be seen by the exposing it by the light, by exposing it to the light. So this we call this solution here. This solution here, we call it here, we give it a name, is normal. I apologize for my handwriting. It's just normal solution, and it has a unique name, quote unquote, stock solution, end the quote. So this is called what? Stock solution or normal solution. Okay, this you cannot see the solute particles anywhere. So with your eyes, or with your experiment by exposing it to the light. So if I said this, then we have second one, a moderate particle sizes, which cannot be seen by the eye, but it can be seen by exposing the solution to the light. This is called colloidal. Okay, can I take this one out? Everybody has it? Everybody has this? Everybody has this? Yes, no, no, yes. Everybody has it? Okay, so take it out. Second one, number B. Solute has moderate particles size, which cannot be seen, cannot be seen by an eye, okay, but can be seen by exposing the solution to the light. So here it is, okay, guys. This one here, this one here, this one here. So here we call it stock solution, stock. Here we call it colloidal solution. Here we call it suspension. No solution, just suspension. No solution. I'll show you in a minute why. So if I have a solution, stock solution, I'll not see anything. Just, the particle size of the solute is so tiny, it cannot be detected by my eyes or by exposing to the light. Now this one here, the particle size, see here, if I put lights here, maybe a bulb here somehow, so light, Just put the light, just the word light, and then put the arrows there. That would be nicer. So creative, light goes through, goes out. This is light. Now, if I put light through this, here the light, I can put light through this, I can see nothing. Okay, guys. So here I can see, maybe put this another color, maybe. I can see those particles. Okay, if I expose this one to the light, I can see the particle. Stock solution, the light will go in and out as is. Correct? Those are still called solutions, colloidal solutions. The both of them solutions. This one here is not solution, not a solution. I'll tell you why. This one here. So I put the light through. I put the light through here. And the light goes there. And this is sitting on the top. I can see, here it is, guys. Okay, guys, so I can see the particles. The particles so large that can be seen by my eyes. So number C, this is A, this is B, this is C. Number C here, number C, particles are very large. Because this is not a solution. Particles are very large and not soluble in the solvent. So we call this one here, we call this one suspension. Suspension. Another example of this suspension is this suspension here. Oops, sorry. This is suspension here. We can call this one here, this suspension here. Oh my goodness. We call this suspension here somehow. This is like charcoal in H2O. Charcoal with H2O. Okay, so that's suspension. And this is not homogeneous mixture, this is heterogeneous mixture. So very large and not soluble. Okay, so not soluble meaning what? Meaning this is heterogeneous mixture. Okay, guys. So therefore, those are homogeneous mixture, correct? So the A and B are our solutions. C we call it suspension. The particle size large. I can see them with my eyes. But they are not soluble. The charcoal on H2O will float, but it's not dissolving, correct? Those called suspension. So suspension is not a solution, but we bring them there because of the particle size of the solute. We are looking at the particle size of the solute. So therefore, they are not part of the really solution. They are heterogeneous. We call them heterogeneous mixture. Correct, guys? So everybody has this. Everybody has this. Everybody has this. Yes. No. Yes. Okay. Can I take it out? Okay. We'll go for number 3. Let me just see what's number 3. according to maximum solubility. That's very important. So according to their maximum solubility. Number 3 here. Number 3, according to maximum solubility. Again, we have 3 ones. We have what? A, B, C, D. A, B, C, not D. A, B, C, 3 types. Well, one is called normal solution. We talked about this. Or stock solution, by which is the solute is at less maximum. So let's post here an example maximum solubility, okay? Maximum, oops, sorry. Maximum solubility, guys. Maximum, that's a real chicken handwriting, sorry. Try my best. So max solubility. So the max solubility of sodium chloride in H2O at room temperature of 25 degrees Celsius is 357 gram per liter. Okay, so 357 gram per liter. So an example here, we'll get an example again. So if I have this is given to me here, correct? This is given to me. Okay, so I will say if normal solution or stock solution, I will have the least. So it will be what? It will be less. Example here, sodium chloride in H2O. So will be less than 357 gram per liter. So if I have less, and this is the key here, this is the key, guys, this is the key here. So this is the word less. This is the maximum solubility. So number 2, how about if they are equal? How about if they are what? Equal. So now we have number 2. So if they are less, then we call this one here normal solution or stock solution. The same thing with the particle size. If they are very tiny, cannot be seen by both eyes or exposing light or any experimental stuff or any tool, that's a normal stock solution. Correct? Number 2, we have saturated solution. So saturated solution, an example of this, example is sodium chloride in H2O will be equal what? Equal the maximum solubility. So in this case here we have, in this case, saturated solution, sodium chloride in H2O is 357 gram per liter, because it has the same amount. When they are equal to each other, this is saturated solution. Okay, Number 3, how about if you exceed this maximum solubility, exceed the 357, you get something called supersaturated solution. Super what? Saturated solution. So, can I, everybody has this? I'll go number 3. Can I have it? Out? Does it? Okay, good. Thank you. So let's take it out. We said what? Number 3. So number 3, we have, oops, let me just do the blue. We started with the blue. So I don't, just to make sure that's, okay guys, number 3. Number 3, I have super saturated solution. Supersaturated solution is the solubility of the solute exceeds, not equal to the maximum solute, exceeds the maximum solubility. So example, I have sodium chloride, correct? In H2O will be greater than 357 gram per liter. So it exceeds. So then in this case here, you get supersaturated solutions. Supersaturated solution. Call it supersaturated solution. Now, with this in mind, supersaturated solution, you will see at the bottom of the container, part of the particles or precipitate that's not dissolved, because that's the whole thing, correct? So, one can see, one can observe a solid, or sometimes called a solid here, or sometimes called precipitate, at the bottom of the container, which cannot be dissolved, dissolved further. So let's look at how does it look like in the lab. Let's look how they look in the lab. So we have 3 test tube. 1, 2, 3. This one here is the solution is not thick, correct? Not thick. Okay. Here solution is number 2. Solution is thick. Here solution is thick, plus you get what? Those particles cannot be dissolved because you reach the max, the saturation of your solvent. The solvent can that much dissolve. After that it can't. An example, here I have less than 357 gram per liter. That's for sodium. We are looking at sodium chloride in H2O at 25 degrees in the lab. Okay, here, this one here, we have a little bit thicker. So that's here very thin. This solution is thin. Okay, so here it is. You can see it thick, like a syrup. So you see the syrup when you put it in the pancake pieces. Put the syrup on this. The syrup is saturated solution. Is what? Saturated solution. So this is equal to 357 gram per liter. Equal. So this is thick, but still a solution because nobody's there. So here is thick, and you have what? You have precipitate. This is that much. This is greater than, this one here is greater than 357 gram per liter. So less than 357 grams, that's the maximum that's H2O can dissolve. In 1 liter H2O, it can dissolve only 357 grams. If you go less than that, you have a normal stuck solution. That's what we are dealing in most labs. So this one here is desired solution. That's what we are looking for, correct? This one here, thick solutions, can be used for special cases, correct? And just very special cases. Thick solution we are not dealing with in the lab that much. Somebody will tell me why we are not dealing with thick solutions in the lab. Why? Somebody will tell me. Well, after a while, the lab temperature are going up and down or something, and this solvent will, this saturated solution turns by time to supersaturated, because some of the solvent evaporate. If you have a cup in your kitchen of tap water, leave it for 1 week, you get it the same size. Put the cup of tap water and then put the label with the marker, put where you started with. After 1 week, you see the tap water the same level? No. What will happen? It will evaporate, correct? Because any changes in the temperature will affect the evaporation of H2O. You will not see it unless you put it in the fridge. Yes, then the volume will not change because everything is there. Nothing will be evaporated. The motion of the molecules is frozen. So put at the minimum, not frozen, but at the minimum. So you will not lose any of your solvent. So, but here in the thick solution, we are not using thick solution in the lab. It's not desired. Not desired. Why? Because after a while, we put them in the bottles, and then we come after 1 month or so, they are already precipitating what part of the solvent is evaporated, and then they have too much of the solute, less of the solvent. They'll start going to supersaturated. So this is super saturated. Okay, this is saturated. And this is just stuck solution. Stuck solution, the normal one. Stuck solution. That's what we are dealing with, stuck solution. Now, thick solution are used? Yes. They are used in thick solution. We can use it in death row. In the old days, they used the electrical shock for people are lining up for being dying, whatever, execution. In the death row, they give them injection, and that injection is potassium chloride, part of it, potassium chloride saturated solution. It caused the heart to pump like unbelievable. So it's the person is just pumping heart, and they put some other chemicals with potassium chloride. So in few minutes, the person just dies out. Are you following me here? So death row people, they take this injection, and this injection most probably will be beside the potassium chloride. But potassium chloride is very crucial because that's what initiate the high blood pressure. Don't imagine. Okay, guys. So we very few uses, but in the lab we don't like it because it's after a while it's just turning it supersaturated. Supersaturated solution, yes, we use it not a lot, but you use it for cleaning the lab. We are what? We are using like dichromate with sulfuric acid, call it the chromic acid. That's a very good acid to dissolve to clean up glassware. So yes, that's for cleaning up. And if you have some calomel pH meters, we use supersaturated solution of potassium chloride. So they have universal cleaning purposes, and for calomel for some equipments they are used supersaturated solution. But the thick solution is not desired. This is just it becomes supersaturated after a while. So now everybody has this. Everybody has this. So let's take this one out and go for number what? Maximum solution. Number 4, osmosis, and then according to we'll take first the electrolytes and then osmosis. So it does not really matter. So we'll take them both, but let's see, because that's the easiest one. And the other one is biology one, by the way. It's very good for biology, the osmosis one. So here it is. Number 4, I'll take the electrolytes. So if you go to the emergency room, what's the first thing the nurses will do for the patient coming, the injuries, whatever? Person had a car accident, bad injuries. What they first do? What they will first do? That's a bag. They give a bag for the patient. It's called what? What's inside the IV? Electrolytes, yes. And did I mention that's one last our Monday about the drinking too much soda is not healthy. Drinking Gatorades are very, very healthy. Therefore, you'll see basketball, then football players, soccer players, you name it, ice hockey players, all those sports, they drink a lot of electrolytes. Electrolytes, they don't have that many acids inside them. Instead, they have electrolytes. What electrolytes are? Those are ions. Those are ions. So electrolytes meaning what? Ions, such as, and those are very important, such as they put magnesium, calcium, sodium, potassium, aluminum, you name it. Those are the good ones. I mean, those zinc. So, and you name it, etc. So those are, but those are the very few. But they don't put heavy metals there, not heavy ions. For example, they don't put vanadium or any of those heavy metals, or they use like gold. Those are heavy metals. Those are very dangerous. Heavy metals. They can cause the kidneys to be collapsed and damaged. They can cause very serious damaging effect for kidneys and to some extent to the liver, but most probably for the they are really attacking the kidneys, so they are not being used. But the lighter ones, So, and did I mention aluminum? Yeah, aluminum is not that toxic. Zinc, but they can use copper. Copper, they can't use it. They can't use copper inside. Those are heavy metals. They can do a lot of damage, mainly for the kidneys and then to some extent the liver. So those are the body is when you have an injury and you start sweating and all the stuff, you are losing a lot of those electrolytes, and those electrolytes are very crucial and very aspect of operation inside the body. Magnesium inside, magnesium is, otherwise you lose it, you lose the memory. You cannot remember anything. And if you have sodium, potassium not there, you get Parkinson disease. You cannot control your what? Your muscles. You start shaking. You cannot take even a cup. You need help for that. So those are very important. The first thing in they give is to give the patient IV bag, which has a lot of those ions, which electrolytes means ions. So we said this. Let's look at the types of electrolytes. We have 3 types. You can see every time 3, 3, 3, 3, 3, 3, correct? So we'll have here 3. So can I take this one out and then just look at this one again? Take it out. Everybody has it. So it is very important that you quit drinking soda and take electrolytes, because as you speak, you lose with the vapors a lot of ions coming out. You lose from the sweat, from anything, talking too much. You lose those ions. They have to be replaced. They have to be replaced. That's the reason they tell you to drink a lot of tap water, not distilled water. Don't come to the idea to drink distilled water. That's no good. Why is distilled water not good? Because it's missing ions. You need ions. You need electrolytes, and tap water has a lot of ions there as well. So it's acting like electrolyte solution, like IV solution, but a little bit less concentration. So here it is. Number 4, we have 3 types. The first type here, we have weak electrolytes. That's number A. Weak electrolytes. If we have weak, we'll have what? Strong, correct? Yeah, that's correct. So strong electrolytes. And number C, not at all. Non-electrolytes, correct? Non-electrolytes. So we said the electrolyte is a compound that's dissolved in H2O and produces iron. Let's do the definition here by itself so we can get this one in our mind. Electrolytes are chemical compounds that are dissolved in H2O to produce ions. This is the definition. Any compound that dissolves in H2O and produces ions is called, the specific name is electrolytes. So weak electrolytes, everything weak you can see in the periodic table. All the compounds are weak except, so here it is, all ionic. Of course, the non-ionic, the covalent, they don't produce any ion, but they produce ion by itself. You have to produce really metal ions. When I say this electrolytes, to produce ions, meaning what? Oops, sorry. Those here, metal ions. That's very important. Those electrons needed in the whole. I mean, you will not believe it if you look at the whole. Well, really, what's controlling the whole body is the liver. The liver is producing all those hormones. Now, those hormones will not work unless they have specific ions working with them. Correct? So you will say here, let's see here, weak, all ionic compounds soluble in H2O can produce weak electrolyte, except let me take those out for the time being, and then I'll come back to them. I'll come back to those here. Okay, guys, so okay, guys, let's look at this. This is weak, we say, except, and this is except group number 1, group 1A, or just 1, group 2A, 1A from start with lithium all the way down, and group B start with beryllium, magnesium all the way down, 2A or 2, plus ammonium. Let me see. No, ammonium is weak. Yeah, sorry. Yeah. Plus strong acids. Plus strong acid. So, which make those our strong acid. What they are? Well, you don't have to memorize it, but at least you will know we have seven strong acids. They are. I'll write the formula, and you can just look at their names there. I mean, I'll like their structure, and then the name you can name it. So you have HCl. This is what? Hydrochloric acid, correct? HNO3, nitric acid. H2SO4, that's sulfuric acid, correct, guys? Hydrochloric nitric acid. Then we have chloric acid, correct? Then you have perchloric acid. How many we have here? 6, correct? 5 or 6? 1, 2, 3, 4, 5. So what's the 7 here? Nitric acid, sulfuric acid, hydrochloric acid, chloric acid. Well, let's just look at this 5. Yeah, let's look at those 5. So nitric, sulfuric, hydrochloric, correct, and perchloric. So let's do those strong acids. Those are example of strong acids. They dissociate and give you strong electrolytes, correct? So the opposite of the weak, strong, which as those are considered to be, those are considered to be what? Strong, because they are dissociating in H2O 100%. So the weak acid dissociation less than 100%. Okay, guys, less than 100%. Okay, guys, so can I take this one out? Can I take this one out? Everybody has it? So now we have the strong acid, and I did not mention there is a strong basis as well. And then we'll come into this one here. Strong acids, and here plus strong basis, which is coming out of group A plus 1A and 2A's. Those will make strong bases. We'll look into them now. So can I take this one out? So we took out, we know that's all weak except group number 1, group number 2. Okay, those are always the ions. They are very strong. They dissociate 100%. So let's look at this. Number 2 here, strong electrolyte. The dissociation is 100 over, is stronger. Dissociation is about 100%. So complete dissociation, not partial, but complete dissociation. The weak are what? Partial dissociation, less than 100. So this one almost 100%. So complete. So you have acids, strong acids, such as HCl, HNO3. Okay, HNO3. You have sulfuric acid. You have chloric acid, and you have perchloric acid. Okay, guys. So strong bases, strong acids. Strong bases, you have group 1A base. Group 1A example from lithium hydroxide. Lithium hydroxide here. We don't need a bracket because we know this they are. Lithium hydroxide, sodium hydroxide, all the way to francium hydroxide. Those are strong, so it's 100%. Or 2A comes from magnesium. I think it is starting with, if you look, magnesium hydroxide, and then you get calcium hydroxide, and it goes all the way to the end of the group. So those are 1A and 2A. They make strong acid, strong bases, and the strong acids are there. So we have beside this another example here, the salts, the ionic compounds made of 1A and 2A metals. So for example, I say potassium chloride. Potassium is there, so I can expect this one here to dissociate to give you potassium plus chloride. The dissociation is 100%. Correct? 100% dissociation. I say calcium nitrate. Okay, calcium nitrate. This group 1A and 2A will dissociate, give me calcium 2 plus 2 nitrates, and the dissociation is 100%. Okay, guys. So that's the strong electrolytes, strong bases, strong acids, and compounds made of group 1 and group 2, 1A and 2A, or 1 and 2, correct? And they dissociate 100%. They are strong. The weak, they are less than 100%. All the elements inside, except group number 1 and 2, all the elements will make, the metals will make a weak electrolytes, and they will make a weak base, or they'll make weak bases. So can I take this one out? Everybody has it? So then we have this is number 2. Number 3, sorry about this. You have to tell me that so I can stop. So number 3 is non-electrolyte. Non-electrolytes. Well, the non-electrolytes, dissociation is what? Dissociation is 0%. No ions. but it can't soluble, but it can be, but these, they can be soluble in H2O, can be soluble in H2O, but they don't produce ions, but they cannot produce ions. This is an example of sugar, correct? Your kitchen sugar dissolved in H2O, correct? But does it make sugar plus H2O? Just dissolve. It's only solubility, so there is soluble, but there is no ions. Here, no ions. Comes out as a molecule. So those are non-electrolytes. They are soluble in H2O sometimes, but they cannot make any other make any ions. If the whole idea is dissolved in H2O and making ions. Well, they can't make ions. Those are not non-electrolytes. Okay, guys. Okay, guys. Everybody has it. Everybody has it. Okay, so let's take this one out. And the last one is osmosis, correct? We kept this one to the last, the best for the last. So, osmosis. Somebody will tell me what osmosis is. Somebody is taking A&P? No. Okay, diffusion of a compound or a solvent from one place to another place through a semi-membrane, correct? Border or semi-membrane layer. So here it is. I'll show one thing here, and you can do this one here in biology. You'll do an experiment. I think we had it a long time, but it will be nice. This is a semi-membrane. Okay. So this is a container here, glass container or beaker, glass container. A semi-membrane, you can say it's a separator. Can be sponge, can be correct, can be sponge, can be plastic bag. So whatever you can use, okay. So can be sponge, can be plastic bag, etc. There's too many of them. We can use one of those. I mean, it depends what type of sponge, but it does have small tiny holes. It depends on the those plastic bags or sponges. How many nanometer their holes inside them. So now we'll fill this one here with H2O, correct? This one here, H2O, and this one, the other one is, the H2O is a little bit here. Let's make it bigger here. And here just, this is H2O with salt. Now after a while, so after a few days or whatever, so it depends on the diffusion. Okay, so diffusion of a solvent from, and this is very important here, from higher concentration to what? To lower concentration. Can we go the reverse? Can we go the reverse? Yes, and that will be called reversed osmosis. Correct. So if the solvent is reversed in its diffusion, then one talks about reverse osmosis. Okay, guys. So if I have a reverse, I have to put the piston here, but I don't want to just hit these guys. If I put here a piston here, that's a piston here. Piston. Try to push this up to this the other way, the opposite way. Piston. That will cause a reverse. So it goes from lower to higher. The amount of H2O here, amount's larger, correct? Amount H2O is too large or too high, whatever you can. Here, amount of H2O is too small, correct? And this one we here, if you put the piston, as soon as you use the piston here to put pressure on the left, on the right side with lower amount of H2O and get it through, okay, now we call it reverse, because that's against reverse what? Reverse osmosis. So now, osmosis is natural, okay? Reverse is not natural. You are forcing it, not natural. That's the difference between them. You are intervening in nature. Nature will tell you always when you have diffusion, it goes by itself. Just do this yourself at the container and put a sponge and put both sides. Is the time up? We have 2 minutes, guys. I gave you a couple of minutes in the long run. We have 2 minutes. Let me finish this one here, and then we'll come back. We have 2 minutes. Pull yourself down. Just pull yourself down. So, where we can find natural, non-natural phenomena, the reverse osmosis. What? Get this, the salt from the sea, correct? Desalination, they call it desalination or desaltination. Here, desaltination, desalination. They don't call it desaltination, desalination. That's one word, desalination. So the desalination is a process very expensive because you have this sponge, those filters they call them, to keep all the magnesium, the hard magnesium and calcium away. It's very salty, correct? Out, and then you get the other side, just a tap water, very nice tap water. So that's a reverse. But natural is you don't have to put piston, you don't have to put anything. It goes by itself. So thank you very much.